example number 1 from your textbook, it's basically the introduction to parametric equations. Now, we're used to seeing things written in terms of y equals some variation of x. All right? And so what we're used to seeing is we're used to something that looks like this, y equals mx plus b. And so what this means is that x is the independent variable, all right, and y is the dependent variable. And so what we do, let me get this off the screen. What we do is we think in terms of function notation. In other words, my x is my input value. It goes into a function, and we'll call that function f, and then it spits out a y value, and that's how we think of it. Now for a parametric, so this is just a regular linear equation, or you'll hear me refer to it as Cartesian. Now, I'm going to write this in a different color. For parametric, can you guys see that okay? For parametric, it's a little different. Here, we get different values. We're going to plug in some value for t, that's the input, and we'll get an x value out of it. Then we're going to repeat that process, and we'll plug in that same value for t and get a y value out of it. Which is a little weird, and so we could call these functions x of t and y of t. So this would be like x of t and y of t. So they're functions of t. It's still graphed the same way though, right? So the graph in either case is going to be x comma y when we go to graph it. It's just, it's subtle, but it is a difference. In other words, we make our x value dependent upon the value for t. In other words, whatever my number for t is, I plug it into an equation. The equation does some math to whatever the t value is, and it spits out my x value. When I do the same thing, I plug in the same t value for an equation that determines my y value, and it spits out a y value. It's an extra step. Now, I can take a parametric equation and turn it into a Cartesian equation, and I can take a Cartesian equation and usually turn it into a parametric equation. Parametric equations are nice for conic sections and finding inverse functions, which is one of the things we're going to do here. So the first thing that we need to do is we're just going to determine the x and y values. So to do that, we just write it down a little differently. So I just make a table of values like I normally would, except I'm going to use 3 columns instead of 2. So I'm going to have t here, x here, y here. And I'm not going to do all of them, but I'll do a couple. So if I say, let's zoom in a little bit. Well, not that much. Can you guys see that okay? If I let t equal -3, then there's 2 things I'm going to do. I'm going to find out what x is when t equals -3. So if I say x is equal to, my original equation is t plus 1, so wherever there's a t, I'm going to plug in a -3. Alright, so do you see that? T plus 1. If I let t equal -3, I plug that in and I get -2. Now, I've got to do the same thing for y. Y was t squared plus 2 times t. So in the next line, I end up with +9 minus 6, or just 3. Now here's the interesting thing. When t equals -3, I'm going to get the point on the graph, -2, 3, because that's my x, y. Now you're just going to have to trust Mr. Adams. The reason we do parametric equations is that because it's easy to find the inverse with a parametric equation. Because remember, inverses, we just swap the x and y values. And so when I go to do the inverse of this, I just swap the 2 equations. That's one of the practical applications of parametric equations. Plus it helps us graph things that aren't normally functions. Notice, I don't know if you'd notice the subtlety, Mr. Adams stopped using the word functions and referred to, equations when I talked about Cartesian equation. Normally I would say a Cartesian function. It's a subtle difference, right? The function has to pass the vertical line test. An equation is just a mathematical relationship that's true. So let's plug in a couple more values. So if I plug in -2, I'm going to take -2 and add 1 to it, so x becomes 1. If I plug in -2 for y, I get -2 squared, which is 4. And then I've got 2 times -2, which is -2, or no, -4, so that ends up becoming 0, right? And so let me just pull up the calculator real quick to show you guys the difference, because you can actually graph Cartesian functions, which you already know how to do, but you can also graph parametric functions. So when I plug this into my calculator, I have to do it a little differently. So these are the two equations, but notice that when I go to plug in a function on my calculator, when it's in function mode, I have y equals. Now if I go to mode, and I come down here, see where it says function? I can switch that to parametric. So if I hit enter, it changes how I enter in my equations. So now I have an x1, y1. So what I would do is I would say t. Now the t comes from just this button here. It'll automatically pull up t. The button that we normally use for x, it'll pull up t plus 1. And then my y value is actually t squared plus 2 times t. Now I'm just going to look at the table of values, and if I scroll up, so in other words, when I plug in -1 for t, and you can verify this later, my xy value will be 0, -1. When I plug in 0 for t, my x value will be +1. My y value will be 0. When I plug in 1 for t, my x value will be 2, my y value will be 3. And so what this means is our x and y values are based on, well, basically this is our coordinate plane right here. These are the points of the graph. And you could plug in more numbers, right? You could plug in the decimals in between, right? I don't have to go from 0 to 1. I can go 0.1, 0.2, 0.3. And if I plug in all the possible t values, I'll get a graph that looks like this. Does that make sense? Okay. And so that's pretty much it. And if I hit trace, it shows up a little different on the calculator. When t equals 0, x equals 1, y equals 0. And then you can see where it goes. If I plug in 2, x equals 3, y equals 8. See how that works? Because the x value is based on this equation, the y value is based on this equation, which are both functions of t, and we're just going to plug in 2 for t, and that's how you get the point 3, 8. There any questions on that? Now, what we might want to know is, what is the Cartesian relationship? Well, let's look at the graph for just a second. That kind of looks like a parabola, doesn't it? Well, if it looks like a parabola, it probably is a parabola. So what's the relationship between x and y? Well, y should be some sort of variation of x squared. So now how do I prove that algebraically? Well, what I'm going to do is grab the right paper and start with these two equations. So if I start with, say, y is equal to t squared plus 2t, and I have that x is equal to t plus 1, this is simple. What I'm going to do is I'm going to plug one equation into the other. I'm going to take this equation and solve for t by subtracting 1 from both sides, and I get x minus 1 equals t. So what I'm going to do is I'm going to take this and plug it into my y equation wherever there's a t. Does that make sense? So I'm going to say y is equal to something squared plus 2 times something. That's why our last section was on composite functions. So what's that something going to be? X minus 1. So then what I'm going to do is I'm going to expand this, and I get y is equal to x minus 2x plus 1. That's this expanded, right? If I say x minus 1 times x minus 1, I get x squared minus 1x plus 1. If I combine like terms, I get x squared minus 2x plus 1. Next, I'm going to distribute my 2 through the parentheses, so I get plus 2x minus 2. Oh, I forgot to write down the squared, didn't I? Then I'm going to combine like terms, and I get x squared. Now here's an interesting thing. This is just a coincidence, but those two cancel out. This is the like term with this one because they're both constants. So I get x squared minus 1. Is that right? So basically what I've done is I've shown that because they're both dependent upon t, there's a mathematical relationship between x and y. This is the hard part. This is what gets students confused. Is how do I go from the parametric equations to the Cartesian equations? It's simple. Just take one of the equations and solve for t, plug it into the other one. Any questions? Yes?
Can you move the paper down real quick?
Like this?
No.
This one?